Okay, so what we have established is that we have written this sample mean as, between, we have sandwiched this sample mean into two such quantities. And then because of the recurrence of I, we have that under each pi. So here we are actually using just the recurrence, not the positive recurrence. We don't need the positive recurrence. First of all, Bn converges to infinity almost surely. Why is that so? This is because what is Bn? Bn is the number of blocks or excursions that can be squeezed in the time interval 0 to n, which essentially means Bn is the number of times the Markov chain is coming back to the state I before the time n. So, and as n goes to infinity, this goes to the total number of times the Markov chain is going to come back to I. And since I is recurrent, this has to converge to infinity. This is a random variable that converges to the total number of visits to I, and that has to be infinity under recurrence, almost surely, of course. So with probability 1 under pi, Bn should be infinity, to converge into infinity. So this is where we are using the recurrence. Another place where we are going to use the recurrence is that the dissection principle. Because of the dissection principle, the etas are going to be IID because each excursion under pi, so there is no conditioning involved here because I is recurrent. So under pi, the blocks are all IID, and this is just a sum in each block. So therefore, the sums of the in each block, they are going to be IID. And the common mean would be expectation of the first block sum, which is this guy, and that we have already computed to be pi f times expectation of the length of the first excursion, the expected block length times pi f, which is finite. So therefore, combining 1 and 2, so what we get is that this ratio converges almost surely under pi to pi f times expected length of the first excursion. Okay, so this is because Bn also converges to infinity almost surely. So therefore, this ratio is going to converge almost surely to this thing, to the expected value of eta 1, which is this quantity. So this is where we are using the dissection principle, and the entire block method relies on the dissection principle. So the blocks are becoming independent, therefore the block sums are going to be independent, IID in fact under pi, and they all have finite mean. Therefore we can use strong law of large numbers. So instead of n, we have Bn, which is a random quantity, but doesn't matter because the random quantity is also diverging to infinity almost surely. So therefore, this thing is going to converge to this quantity by strong law of large numbers under pi. I would say this is the key step of the proof. Once you approximate this using the block sums, once you bound it from both sides, this is the key step. So let's just review what we have achieved. So we bound this sample mean by two such quantities. And then we show that this quantity here converges to this quantity. And similarly, of course, since Bn is going to infinity, this quantity here is also converging to the same thing. So therefore, because of star, because of these inequalities, our proof would be complete provided we show that these converges, Bn by n converges to the right thing, namely Bn by n converges to the 1 over expected block size, which is 1 over expected length of the first excursion. If that happens, then this also will converge to the same thing, and therefore both will converge to pi f. So this is the only step that is remaining. So therefore, now let's try to prove that this happens. Now, intuitively, as I said, this is obvious because if you look at n over Bn, n is the time point up to n, and Bn is the number of blocks up to time n. So n over Bn should give you the expected length, So you have Bn many blocks up to time n. So therefore, n over Bn should give you average size of the blocks. Right? N over Bn is the average size of the blocks up to time n. And that average should converge to the average expected size, block size, right? So therefore, that is because the blocks are also independent. So each block is independent. So the block sizes are IID also. So therefore, n over Bn should converge to the expected block size, which is expectation of tau I1. And therefore, Bn over n should converge to 1 over expected block size. So this is the idea of the proof, but let's just write it down. So since I is positive recurrent, under Pi, the block lengths, this is the block lengths, alpha 1, alpha 2, alpha 3, and so on. Remember, that's how we define them. The block lengths are IID. Now, for the block lengths to be IID, you don't really need I to be positive recurrent. I recurrent is enough. But then I write that these are IID with finite mean, which is the expected block length, which is expected length of the first block, which is a expectation of tau I1. So to say that it has finite mean, you need the positive recurrence. Now, therefore, this converges to this expectation by SL, standard strong law of large numbers. Now, what is this? Is so the tau n by n is essentially sum of the alpha s from 1 to n. Okay, because this sum telescopes, and that converges by SLN, and I said, to the expected block size, which is expression of alpha 1, which is expression of tau I1. Okay, now use the inequality that tau I Bn by definition is less than or equal to n, because Bn is the last case as the tau I k is less than or equal to n. So therefore, this is less than or equal to n. And Bn plus 1, tau I of Bn plus 1 is strictly bigger than n. So therefore, from this inequality, we just divide this inequality by Bn. So that will give you tau I Bn over Bn on the left hand side. On the right hand side, you will have this divided by Bn, but then you adjust it, because this is Bn plus 1, you adjust it by Bn plus 1 over Bn. Okay. Now we know that Bn converges to infinity, almost surely. That's because I is recurrent. Again, we are just using the fact I is recurrent here. So I is positive recurrent is only used to use the fact that this has finite mean. Okay. Other than that, nowhere else is used in this particular part of the proof. I is positive. Okay. So because Bn converges to infinity, obviously tau Bn over Bn will also converge to this expectation. Similarly, this quantity will also converge to this expectation, and this will converge to 1 because Bn is converging to infinity. So therefore, again by sandwiching, we get that n over Bn converges to expected length of an excursion. Therefore, Bn over n, of course, will converge to 1 over the expected excursion. So that completes the proof of the strong law of large numbers for Markov chains.